When we were building linear models, we made some assumptions about relationship between x and y. We had these four assumptions, and we said that we only can say that coefficients of the linear model are correctly estimated, calculated by the estimation process if those four assumptions are not violated. Sometimes, even if those assumptions are violated, the simple transformation of the variables or scales on which those variables are measured can bring things back to the linear relationship. And in this case, we just change the variables, we change the scales on which variables are measured, we rerun the linear regression, and then if we want a prediction, we just transform back to the original non-linear scale. The most common two cases of models that are not linear but can be made linear by changing the scale is the power relationship and exponential relationship. So let's look at one of those examples where relationship is not linear, but by changing the scale we can make things linear. So first example is multiplicative model, when y and x change in the multiplicative through multiplicative formula. So y is just ax power b. And such relationship arises, for example, when we try to understand change on the percent scale. So in other words, if you're interested, how the so let's say x is price, and y is sales. And instead of asking if I increase price by $10, how much my sales change, I'm gonna ask the question: if I increase price by 10%, what is the percent change in sales I'm expecting to see? So in other words, I want to know if I change x to alpha x. Let's say alpha is 1.1, which is the same as increasing x by 10%. Then y will change from ax to the power b to the a alpha x to the power b. And I'm going to divide both sides here by ax to the power b. So I'm going to have 1 alpha to the power b. So in other words, if I increase x by alpha, my y will be increased by alpha raised to the power b, and again increased on the multiplicative scale. So this relationship is not linear, but I can make it linear by applying the log. So let's take the logarithm of this formula. So on the right hand side, I'm going to have the logarithm of y, and on the other side, I have the log of the product, ax to the power b, and we're going to use the property that log of the product is just sum of the logarithms. So it's equal to the logarithm of a plus the logarithm of x to the power b. And we're also going to use another property of log that says that if you have something raised to the power on the log, then this power can just come in front of the logarithm, meaning that it's just equal to log of a plus b log of x. All right. So, and actually the relationship are linear now. So, but on the logarithmic scale, logarithm of y is linearly related to the logarithm of x. So we're back to our linear model, and again the log of a is our beta 0, and our beta 1 here is just the coefficient b. And this coefficient b, or beta 1, is called the elasticity, and this elasticity changes the percent of change in y versus percent of change in x. And when variables are related to the multiplicative scale, when we put them on the logarithmic scale, then they become linearly related in an additive fashion. And in R, you can just type this the same lm command, and instead of regressing y on x, you regress the logarithm of y on the logarithm of x. So you find the regression line on a logarithmic scale. Okay, if you have situation when things change on the multiplicative scale in the original data set. Another example, the exponential model. So y is just an exponential function of x, and there are a few examples when this happens. So one example is the compound interest. And interest. So if X is the duration of your investment, and A is your initial investment, and B is your return rate, then Y is going to be return on your investment after X and whatever units of time you use, let's say years, after X years. Okay. Another example of the exponential relationship is spread of the virus. If your rate of spread is greater than 1, meaning each person spreads to more than one person, then you have basically this explosion of the virus and everybody in the world will get it eventually. And if your transmission rate is less than 1, meaning that each person on average gives it to less than one person, then over time the virus disappears. Okay. Growth of the population. So if 2 people give birth to more than 2 children, then you have this exponential growth of the population, and vice versa. If 2 people give birth to less than 2 children, then you have this decay in the population, and eventually population will disappear. Okay, so there's a lot of examples in real life when things are related through the exponenta, and we can make this relationship linear again by taking the log on the both sides. So you have the logarithm of y on the left hand side, and on the right hand side you have, again, we use the property that the let's write this down. So the log of y is the log of a e to the power bx, and we're going to use the property that log of the product is the sum of the logarithms, so it's log of a plus, and now it's going to be logarithm of e to the power bx. Again, we're going to use the property that if you have something raised to the power, it can become in front of the logarithm, so b times x is here, and then we have logarithm of e, which is left, which is just 1, because this is logarithm of the natural scale, so that becomes our relationship. The difference between the previous case is that x is measured on the original scale here, so you only have to put the y in the logarithmic scale. And if you put y in the logarithmic scale and the relationship is exponential, then it becomes linear relationship. The caveat here is that y has to be positive. The logarithmic function is not defined for negative numbers. The dummy variables, when x is either 0 or 1, cannot be also logged just because of that. They can take values of 0. And usually counting variables, so variables that count some items, usually left as is. We don't put them on the logarithmic scale. Let's look at a concrete example when we can apply those transformations to make things linear. We're going to look at the mammals data set. And mammals data set has 3 columns. So the name of the animal, then size of the brain measured in grams, so, and then size of the body measured in kilograms. All right, and the command head will print us the first 5-6 rows of the data set, and command tail will print the last 6 rows. So this data set has 62 observations, so 62 animals. And for each of the animals, we have the brain size and the body size. And let's do the scatter plot of the body size versus the brain size. So we try to see if things change linearly here. And well, you kind of can spot a couple of problems here. So we have this observation, which looks like outliers, right? So the distances here are small to the line. Distances to line are small here, and here they are large, right? So this distance is large. So we have this violation of assumption that distances across different values of x have to be the same. And also, if you look at the residuals versus fitted value, you remember we want this dashed 0 line, and we want things to look like white noise around this dashed zero line, and they simply don't, right? So we have large residuals here and smaller residuals here, so things are not normal. The variances are not constant, so there's clearly violation of the normality. And if we do our diagnostics plot, this residual versus fitted that you've seen on the previous slide, and this is our QQ plot that tells us that yes, indeed, we have few values that violate the normality assumption. Looks like we have the we have 1 and 2, so we have 2 influential points, and we have 1, 2, 3 outliers and 2 influential points, and those outliers violate the normality assumption. So a lot of the assumptions of the model are violated. So we have to try and see if we put things on a different scale, whether we can make things looking more like linear relationship. So we put both things on the logarithmic scale, and voila, let's look look what happened to the plot. Things look much better now, so they more resemble the linear relationship. And the residuals, so look at the residuals, how they vary across from the fitted line. So it looks like we have similar pattern here and here. Well, you have an outlier here actually, but outside of this one outlier, things look much better now. And if we look at our diagnostics plot, well, yeah, so the residuals versus fitted seems very nice. We have a couple of outliers, 11 and 34. Can you guess what those outliers are? Well, one of the outliers is human. Humans have disproportionately large brain, and another outlier, we'll talk about it in a few seconds. So a few outliers that violate the normality assumption. Looks like no leverage points, no influential points, but otherwise things look much better. So let's look at the coefficients and let's try to interpret them. So the intercept is 2.1, meaning that, well, actually, the intercept is hard to interpret here. The interpretation of the intercept here, if body or log of the body is 0, then we're gonna have this value for the logarithmic. Then the log of the brain is 2.1. Well, it's a meaningless statement. So if log of the body is 0, it means that the body itself is 1. Yeah, I'm not sure what. So I'm not sure if there's any interpretation, but this number has interpretation. So remember, on the log scale, this is elasticity, or it basically tells us that if your body size changes by 1%, your brain size should change by 0.7%. Okay, and let's look at the outliers. So again, the observation number 34, which is a man, is an outlier, as we expect, right? The humans have disproportionately large brains to the body size, and another outlier is actually chinchilla, and chinchilla has larger standardized residual compared to human. So chinchilla is almost 4 standard deviation away from the predicted value. So chinchilla has disproportionately much larger brain than humans as related to the body size. So that's we should be very suspicious about this. Why chinchilla has such a large brain, and actually this is deliberate here. So it's actually so if you look at the brain size, 64 for the chinchilla, and the body size is 0.425. So you actually can see that there is something wrong with this observation here, and actually it's an error. So the brain size of chinchilla is 0.065. No. It's 0.64. So it's actually 100 times smaller than reported in the data set. There was simply an entrance error in this data set. And once you fix this error, actually chinchilla becomes not that impressive, and human essentially becomes the largest outlier in the data set, which means, humans essentially are the master race for supreme intelligence.